So let me introduce Michael O'Sullivan from Cadence Design Systems. He's the Engineering Group Director. He's got a focus on verification and is based in Edinburgh, Scotland. He's been with Cadence for over 27 years in various roles in sales, marketing and design services. Prior to Cadence, he was a design engineer at SD Group in Dublin. Over to you, Michael.
Thank you, Julian. Thanks for attending. Thanks for coming to the after lunch session. If you think you're going to learn anything about FPGAs in this session, you'll be highly disappointed because that's not the purpose of this talk. So Mike Bartley asked me to present at an FPGA event 2 months ago, and I said, look, we have a FPGA solution, but I'd rather talk about what people are doing worldwide in the industry today for prototyping and emulation. Just I says I can give a better view on that. We have a product, but it's not for FPGA guys, what probably most of you do. So look at this as kind of a view of what people are doing in the world, what kind of chips. You saw Sean Redmond present today on hyperscalers. They're probably the biggest consumers of prototyping in the world today. They spend millions on it, okay? I won't say billions, but millions. You'll see the size of some of the chips that these people are doing. Automotive industry, virtual prototyping has been around since I was an engineer in Philips in the 80s, but it's on the way back now because automotive, people want to write software before the chips come back, before the cars come back. It's all picking up. And again, just to echo where Sean was talking about this morning, you know, this is the golden time for in electronics, right? You know, he may have said the UK or Europe is small, but everything, electronics is in everything. There was a Swedish sales guy 20 years ago who used to do Bluetooth sales, and he says, people want Bluetooth and everything. They want it in toasters, they want it in washing machines, and why? But it's everywhere today. It's everywhere. So just take this as kind of a general. It's not flicking again, Jill. Oops.
Still not flicking?
No.
Nope.
It's flicking on that.
Doing it on here.
I had this with a customer on Friday. So. Again.
Let me see.
Yeah, it's
right.
Good.
I'll just flick it from here.
Yeah. So you may not see some of the slides on the right. It's okay. So Cadence. I go to events. No one knows who Cadence are. Cadence is calls itself now an AI computational software leader. Cadence is an electronic design automation company. That's the old definition, and I'll stick with that in this audience. It's all about automation. You know, Sean put up the growth numbers, but it's just about automating how to let chip designers, verification guys, electronic engineers automate what they do. When I was an engineer, I did digital design. You designed it on a piece of paper, you drew out the gates, you drew out the flip-flops. Then you used tools from Mentor to enter your schematics, which was the most boring part of your job. But then Synopsys came along with synthesis and all that. So it enabled people to do huge chips. It's all about automation, enable engineers to do more and more. I mean, in the early 90s, 20,000 gates, 50,000 gates was a big chip. Today, people talk about 60 billion gate chips. It's absolutely crazy what we're doing. So just to talk about Cadence, I mean, this slide is probably from 6 months ago. It says 13,000, there's 15,000 people today. So Cadence is accelerating into various different industries. It's all about growth in companies. You want to grow. Chip business is one area, chiplets is another, IP is another, systems. It's all about growth. And as you can see, Sean presented how big EDA companies have grown. So Cadence in 10 years have gone from a $2 billion company to a $4 billion company. That doesn't come easily. There's a lot of work goes into that. There's a lot of acquisitions and people that we're going. And then everything has got an AI label. If your company doesn't have AI at the end of it, you're not living in 2025. So we have various products that go from digital design, analog design, which is our forte, system design, and then we have our hardware boxes, which we'll talk about today. And we've got system design, 3D IC, PCB, and we're getting into things like drug discovery and using different ways. And AI will drive all this in the future. I mean, AI is going to happen. Someone asked me in my booth today, I says, what do we have today? And we have simple tools that we're working on, but In 5 years' time, everyone will use AI. Everyone. Just get on board. That's my plug for today. So the agenda for this talk is easy. Where do people use emulation prototyping in the semiconductor industry? Okay. Once I was in Eindhoven and AMSL have a stepper, and someone wanted to virtually create a virtual prototype of the stepper, and I'm going, for what? You know, there's got to be a reason. So that's why I tied it down. We want to model the semiconductors. People use prototyping and emulation to de-risk their silicon bring up. One is they want to make sure that all that means is, well, is the software going to run on the silicon when it comes back on the board? That's what people pay the money for. It's not for anything else. So if you can do that a different way, people will do it. If it doesn't matter that your chip comes back and you can develop your software there, people will do it. But if you want your chip to come back and you want to be 100% sure the software is running, you will invest in emulation and prototyping. I'm going to talk about Cadence platforms. It's not a sales, it's just to show you what we have. I can't talk about what the competition have. Look at their websites. So it's just good. So again, Sean showed today the cost of doing chip design is astronomical now. I mean, Sean was talking at 1 nanometer, $1 billion. Why is this the case? The main reason is the complexity has gone up. Think about what goes into a 2 nanometer chip, 48 billion gates. How many state, if it's pure digital, the amount of state spaces you have to verify, it's phenomenal. So you have to put more effort into verification. And verification is not a defined art. You cannot come up to a guy and say, is the chip fully verified? The answer is no, because verification means the job of a verification engineer is to find more bugs. And they will find them if you let them long enough. So, but you want to tape out, so you have to have some confidence. And then the software content is growing. Look at cars today. It's all about the software, right? So software is astronomical. How do you verify? How do you verify that software works with your hardware? How do you make sure that when that chip comes back on the bench and you want to release your product, that the software is working? You don't want to start your software development cycle the day the chip comes back on the bench. So how can you accelerate it? That's what we're talking about here. And how do I verify it? It's not rocket science. It's been around for ages, except the problem is huge now. And I think Sean, I liked his word, cost of failure. What's the cost of failure? You get a 2 nanometer chip wrong, forget about the cost. It'll probably be 9 months, a year before you get the other silicon back. That doesn't even include your respin for your development. It's cost of failure. You get one shot at these things. You will see surveys that says, oh, silicon respins are gone the way up. They're not gone up at 2 nanometers because cost of failure there is just too high. Again, I just want to show you this. This is not to say everyone does verification different. Everyone defines their chips different, you know, but basically IP, subsystem, chiplet, and SoC. And this is a worldwide view of the world, right? So people today, when they talk about chiplet, SoC design, they're talking about chips that can be up to 40 billion gates. Absolutely huge. The hyperscaler chips are this size. Okay, and I'll show you some more when I show you the Cadence emulation. The subsystems that are developing are like almost 1 billion gates, and the IPs are huge as well. So things are getting bigger and more complex. I mean, there are people in the world who do smaller chips. Yeah, there's nothing wrong with that. But these guys are driving, as Sean said today, the fabs. These are the chips that are filling the fabs. These are the chips that are selling in volume. These are the chips that are powering the data centers, that are powering the AI revolution. So this is huge business. These are the challenges that Cadence is working on today. Okay. Simplified view of the world. You know, how do people? What do people do on the chip side when they look at emulation prototyping? What do they do on the software side? So, you know, in the RTL world, unit tests, design and tests, people don't do much prototyping emulation there. They do that in simulation. But then when they start moving up when they want to bring that SoC up, they start bringing in emulation and FPGA. Emulation is good for, you have a fast bring up, you have full visibility. FPGA gives you a bit more performance. I have a slide on that. Then people start using the emulator to do kind of some system analysis. What's the power envelope of your chip? How can it design the package better? Those kind of things. And then you can start doing system level tests, because once you go to an SoC, you can forget about UVM and all those verification techniques. You need to start driving software onto the SoC. You start using some real use models. And again, that's it. And then for the big chips, people, you can do DFT on the emulator, but it's probably not a good use of it, okay? Software guys are much more simple. They just want a model. Doesn't matter whether it's virtual, prototype, or emulator. They just want a model early that they can write their software, boot their OS, and see that all their software is working. Software people are not, they very seldom do they say what kind of model they want. Sometimes speed comes into it, but for writing software, if you can run it at 1 megahertz, that's probably 99% certain. If you want to do a demo of your live system, that's a different model. That's not what we're talking about today. But again, the software guys, for example, the emulator is not really meant for software people, but there are companies in the world, big GPU companies, who just write all their software on emulation because it's easy. The debug capabilities are amazing, but they have very deep pockets. So yes, they can do that on emulators. Very few people do, okay? This is a different slide to show the same message, you know. At the IP level, simulation is good enough to find all your bugs. When you move into the SOC level, acceleration, emulation. But for hardware software development, if you want to see that your hardware and software are working together, you need emulation or prototype. Okay. I always look at emulation as the first phase. You can bring up your RTL, you can compile it fast on your box, and you can debug everything. When the RTL is more stable, it's easy. You can compile it, put it on the FPGAs. You can leave it there for a few weeks. It's a much slower process. But people pick and choose what they do. And the next slide, I think, will show that. And then you can still run your stuff after you tape out and do system validation right up to when your silicon comes back. Some people do a lot of post-silicon work on the emulator as well to help them debug. So always shift left, but yeah, we've been talking about shift left forever, okay? What you find out is people just try and do it faster, quicker, but chips get more and more complex and means the schedules get longer and longer. So yeah, I have yet to see the shift left shortened project life cycles. So this slide is about, I would say, 10 years old, but it actually is probably the best view of what you can do out there and why, okay? And I suppose the one message is there's no one size fits all. Every chip has got its own use case and how you verify it, what you use for emulation, prototyping. So virtual platform, which is basically a system C version of your design, runs very fast. It's out before the RTL, so you can start writing software immediately, no registers. Great to debug because you have access to everything, and you can create a virtual platform and copy it to 2,000 software engineers. Okay. Biggest disadvantage is it's probably gets out of date very quick and people don't keep it up to date. But there are companies in the world who do use virtual platforms a lot. And I would say in the last few years, the companies that have brought virtual platforms back on the market are the automotive companies. They want, because software has really expanded, and I'll show you a slide later on what Cadence has done into writing more software, and this is a very easy way of bringing it up. Formal analysis we won't talk about, but it's a mathematical way of creating stuff. It's exhaustive, but it's not scalable. CPU designers use formal a lot. You won't use it to verify your SoC. I would say expanding, but niche. Simulation is the workhorse of the semiconductor industry. Everyone will not tape out a chip without running some form of RTL simulation. Okay, it's accurate, good debug, available. You can get it everywhere. There's no free simulators yet on the market, so keep us in the job for another few years. You can do mixed extractions. It's not good for software debug. It's too slow. We've tried. We try and do some kind of hardware software simulation, and it's too slow. Okay, hard to debug. So that's why Cadence has been in the emulation business since it a quite quick turn. So it's a well-known model. The reason emulation became important is this was too slow to debug software. So people came up with emulation. Obviously, disadvantages. You can't compile anything until you've written some RTL. That's good. It's good to debug because you have access to every single register. Emulation normally runs in the 1 megahertz range, no matter what anyone else tells you. And that's deliberately architected over the years. They've gone for scalability and keeping the power down rather than increasing the frequency. And that seems to work for software guys. And that's the main purpose of this. This is obviously, I don't know why an EDA vendor would say expensive to replicate. It means emulation is an expensive investment in your company. I call FPGA prototyping. I'll explain the word I use in Cadence later, but it's you can get up to 5, 10, 20 megahertz. It's only stable after the RTL. You don't want to be messing about with RTL and prototyping. It's okay to debug. You don't have full access, but we're trying to change that. And it is more expensive than software to replicate, but much cheaper than emulation. And then you can buy prototyping boards and use them as well. So you have multiple things, and there's no easy answer to what to use, okay? But I would say for emulation, those hyperscalers, they don't have much choice. So today I'll just focus on what Cadence has to offer on these platforms, virtual platform emulation prototyping. So I think I've alluded to some of this, business challenges, time to market, reducing cost, technical challenges. I suppose summary, it's just getting more and more complicated. A lot more cores, a lot more interconnects, multiple IPs, subsystems, software, getting people to work together. Lots of software. Software drives everything, okay? You can't just do a silicon. You'll have a software team involved as well. I just wanted to show, this is an example of some form of automotive chip and software. You can see how complex it is. You've got GPUs, EPUs, you've got multiple interfaces. Software is really complex for automotive now. This is a really complex chip. It's a complex ecosystem. And you're bringing it into an area that's not used to doing such verification, not used to bringing up such software. Cars have changed a lot. So there's many ways. So virtual platform has come back into automotive. It's an easy way to bring up multiple platforms. So I call that virtual platform. Hybrid is where you can mix and match your System C model with RTL. You can even bring in emulation and prototyping. Okay, so virtual platforms have been along, but they're loosely timed. You can OS boot. We use virtual platforms with our emulator to boot OSs. It's available early. You've got access to all the registers. You can write your software, and companies do this today. Okay, the hybrid platforms, you can bring in RTL for your DUT. You can do a lot more accurate, and then your balance is accuracy versus speed, and you're more confident that the chip, the software you're writing for, will work on the chip that's coming back. Okay. And Cadence is a full platform, Helium. Obviously, you need models for virtual platform. So every IP, say your PCI Express, you need a model. You need some form of assembly. So basically, how do I create a virtual platform without having to instantiate? So write some IP exact and build it up. Then you need some debug, and then you need it to, at some stage, you want to do hybrid. You want it to interface to the simulator, the Palladium, or the prototype. And I'm not going to go through this, but if you read in the news, Cadence has acquired VLab Works in the last month. So they basically do virtual platforms for the automotive industry. So that's what I'm saying. I didn't know about this until I found out probably 2 weeks ago. So again, our customers are asking for more and more of this. So they're mainly based in Australia. So if anyone wants a job there, just go there. So Cadence always had an emulator. It has dabbled in what I call FPGA prototyping, but not very successful. So customers have told us we have multiple challenges doing FPGAs prototyping. These are not the customers who have got 20 FPGA experts who can create multiple FPGAs, do systems, and do it rapidly. These are people who don't have that expertise at the time. So they challenged us, the EDA industry, to come up with a way of making this easy. So what we did was, you know, too much gates, too much memory, too many peripherals, not enough time, needs to be. So what we did was, Cadence has a history of doing a compiler for emulation. So what we did was, we did the same for FPGA prototyping. We basically used the same compiler, we took the RTL and just map it to FPGAs. We have an architecture that works, okay? You don't have to touch the RTL, feed it in, does Vivado under the hood, does all the time enclosure, and then you can connect it into the Cadence ecosystem. So I'm just looking at the slide. And I call that enterprise prototype. The problem with this is you can take, say, a 20 million gate chip and do it very quickly. And if it runs at 4 megahertz, it runs at 4. But you're not going to go in and tweak anything. You're not going to partition or get into Vivado to make it run at 8. 4 is your number, and that's it. And that's perfect for software guys. That's perfect for people who want to run FPGA prototyping after their Palladium box. If you're doing a demo of a system, that's not good enough. You still need to go, but you're not going to do a 40 billion gate chip on your own custom FPGA boards. You just ain't going to do it. Marketing slide, but the thing that's important is this is our Palladium box. These are actually Palladium Z2s, and I'll show you Z3 in a minute. But if you look at who uses emulation, 9 of the top hyperscalers, 15 of the top, 4 of the top mobile, probably 5 now actually. But what I'm saying is all the big companies use these technologies to get their chips out. Yeah, they may complain that they have to invest a lot of money, but yeah, there's no other way of doing it, okay? So these are our Palladium Z3 boxes. So this is a full rack. This is about 2.5 billion gates can fit in this, about 2 billion on the Protium X2. So these are boxes you put in your data centers. You connect them up and you use as is. Again, just for Palladium Z3, we actually develop it's a processor based. So basically it takes your netlist and maps it into a set of instructions. It's not FPGA based, and the Protium X3 is based on the VP1902 from AMD, which came out at the end of the year. And it's all about automation. And then for Palladium, it's about early compile, fast debug, and then you kind of shift it over then to the Protium. Not everyone will do it. Some people buy Protium because they just want automation. They just want to run software. Again, everyone does it differently, okay? Then because we got so focused on size of boxes, these boxes got very big. It became harder to sell them to smaller companies who do smaller chips and who used to use earlier versions. So we came out at the end earlier this year with Palladium Z3 that will sit in your desk, doesn't need any cooling, 128 million gates. I think you can have 8 concurrent users. You can connect all. So it's something for people who do smaller chips and who want to do that emulation before the silicon comes back. Non-expandable, but you have to make some compromises. So, okay. Again, this slide, we have this modular compile. So basically, as chips get bigger, we don't want the compile time to increase. So we came out with a technology that basically says at a certain point, it will stay, the compile time will stay the same. But the thing about to watch this on this slide is, on our current version of Palladiums, you can connect 14 racks together to give you 48 billion gates. You can't go beyond that. And I would say our customers are looking way beyond that. That's how much the industry is changing, okay? This is just to show you the trends in the industry, and go back to Sean's. It's exploding, guys, and it's exploding in the Far East and in America, and I don't see it stopping, okay, unless Donald Trump decides to intervene somewhere along the line. So again, I'm not going to, we full debug on Palladium, we full debug, but we also realized for FPGA prototyping, software guys need some form of debug, so we've invested a bit in that. So we've just used all the standard techniques, and works quite well. Many different models for using emulation. The standard one was in-circuit emulation. That one is kind of moving away. Everything is going virtual. mainly driven by people putting these boxes in data centers, so that they don't want to be going in, changing connectors. They want to do everything. But there's multiple models. People, assertion based, they do dynamic power analysis. There's multiple ways to use a Palladium. Okay, so jobs for life. So yeah, summary of the Cadence solutions. You have our emulator box, you have your protein box, and other vendors have the same, let's be fair. And then you have a whole solution and apps around it, like you can have speed bridges, which are kind of changes, you can connect up PCI Express and it changes the data rate so you can use it. You got virtual tests, you got virtual AVIPs if you use VIPs for simulation, memory models for connecting up to memories. You can have a job scheduler if that's the way you want to do it. Power analysis 3.0, which is huge, dynamic power analysis. You can now do real number modeling on emulators for small PLLs, but certain analog companies want to do that. 4-state emulation used to be 1 zeros, now it's X and Zs. You can do fault emulation, but that again is a smaller market. And then you can connect up the virtual platforms to the Palladiums, and you can do things like you can boot an OS and then on the virtual platform and then swap over to the emulator. There's multiple things you can do. So just to summarize, you can't say software is becoming more, it's becoming more important than ever. It continues to grow. It drives everything we do. If you look at a car today, it's defined by its software. That's what most people complain. But it's huge, the amount of lines, how you verify them, how you do it, how you get your product. So that's what's driving all of this, okay? Software, hardware verification. People are doing more and more in the cloud. So you have to take that into account. And then going back to the slide, one size fits all. You do whatever you can at various stages of the project that suits whatever the goal of your company is. Some people use virtual platforms, some people don't, some people use emulation, some don't, some use prototyping, some don't, some use all. So it's up to you. And obviously with all of these technologies, it comes at a cost. So you have to do your own ROI. And as Sean Redmond said this morning, there is a cost of failure. What is the cost of failure to your company to miss a bug or to not have the software running when the chip comes back? So yeah, all complex answers that I can't give the answer, questions I can't give the answers to. With that, that's it. Gillian, thank you.
Thank you
Any
very much.
questions or?
Any questions online?
Yes, so cloud-based solution on the slides. Does it mean you don't need to buy any hardware anymore?
No, you can buy it, and we have a data center in Georgia. That's where we have one, and it's cheapest electricity, by the way, in the US. Yeah, you can buy it there.
Do you offer it as a service?
Yeah, if you say a service, I would like to have 2 racks of Palladium for a year. Yeah.
Might work out cheaper, I guess.
Cheaper is a relative term. It depends. Yeah, what you're basing on. You're not paying for any electricity. You're not paying for any data center. So yeah, it's more convenient than having to do all that yourself. And then the big thing that these Z3 emulator boxes need water cooling. It's just and a lot of data centers don't have that, so it's easier. But it works. So we have many customers. Okay, so. Okay, thank you very much.
Next slide.